Good morning, everyone. Myself, Durga Bhavani, working as an assistant professor in Marri Laxman Reddy Institute of Technology and Management. So today we are going to discuss about a DA subject. So in that, I am going to tell you about a single source shortest path algorithm. So first of all, what is the main specification? What is the main intention of a single source shortest path algorithm means? Whenever we wanted to travel from one place to another place related to source and destination with a minimum cost. So for example, let me take, so I wanted to travel from A node to B node. So here with some particular distance, some 2 meters like that. So these two are called as a nodes, and this is called as a cost of vertex, or these are also called as edges and cost of vertex. So how we are now, the main intention behind this single source path is nothing but to calculate a shortest path. So as we are choosing only one node and we are traveling to a different nodes, so all nodes we has to take only one particular node so that we can travel all other vertices to which preferably gives a shortest path. So in this we primarily discuss about a 4 specifications. So first is a single source shortest path, single source shortest path problem, and here we will going to discuss about a pair, source, destination and all pairs. So pair in the sense, so we are going to combine, so from A to B, again B to A. So like that all the combinations we are going to check one by one. So here only single source means we are treating only one node as a major source node and remaining all are the destination nodes. So here destination path in sense, so where we wanted to reach. So all paths in the sense from each and every vertex we are treating as a source and we are treating each and every vertex as a destination. So main intention behind this single source shortest path is, so here we are going to use a Dijkstrau algorithm. So here we does not find a minimum spanning tree. It is designed to find a shortest path in a graph from one vertex to another remaining vertices in graph. For example, let me consider A node, B node, B, C. So like this. So I wanted to travel from A to B, B to C, D to D. So like this, I am having some certain node specifications with particular distance. So now I don't have a path from A to C, but I have a path from C to A. So here, if I choose this is my source vertex, so that means I wanted to travel from A to D, A to B and A to C. I wanted to check which path is going to give a minimum cost. So that is the main intention. And in this, I cannot go backward direction. Suppose I am checking from A to B, so A to D and D to B. Again B to A. So in this form, I'm unable to touch the C. So what is the specified path? A to D, D to B, B to C and C to A. This is the specified path here. So again, if I'm supposed to change, I cannot start from here. Again, I want to start from a initial step. So that is the main situation scenario behind the single source shortest path algorithm. So the definition is, the Dijkstrau algorithm is designed to find the shortest path between two vertices. So only two vertices, the shortest path between two vertices we are going to find. So suppose in a given graph, so V is the vertex and E is the edge in that particular graph. So we are going to calculate the edge of a matrix or cost of a graph. So here the main it will help for a optimization of distance, time and consumption and protocols, as well as data packets and optimal access path for all central resources of all the processes. So in these specifications we are going to check, it will be useful, this single source or shortest path algorithm. So here we have two types. So that is nothing but Dijkstrau algorithm as well as a Flody-Walshall algorithm. So this Flody-Walshall algorithm is also called as a all pair shortest path, and single source shortest path is also called as a Dijkstrau algorithm. Let us take, this is one particular graph. So this graph is nothing but a undirected graph. So that means how we can tell this is a directed graph or undirected graph means, so when we are having specified direction from one node to another node, it is called as a directed graph. So when we are having a when we don't have a direction, so that means it is not indicated with the specification of arrow mark, it is called as a undirected graph. So this is an example for undirected graph. So here I am taking a source vertex as a S and destination vertex as a E. So I want to travel from S to E. So I have multiple sources. So I can also travel from S to A to B, B to C, and C to D, and again E I can come. And here loops same as it is MST, like looping should not be done, and it should we has to visit all the nodes at least once. So I can also travel in another part, like let me check, like S to S to D, D to E, E to C, C to B, C to A. So like this I can have a possible number of optimal solutions. So in this I wanted to choose a best solution which is having a less cost. So let me take here, so these are the vertices, and here whichever having no connection, that written as a infinity, which are having a connection, that are written as a values. So let me check, like S to S is 0. So S to A I have a distance called as a 6. So that is nothing but S to A I am having a 6. Again S to B I don't have any connection. S to D I have a connection. S to C I don't have connection. S to E I don't have connection. So like this. So when I am traveling from S to A, so the cost is 6. Again S to C, the S to D, the cost is 8. So I don't have a connection from S to B. So when I am not having a connection, so when I don't have a cost from S to when I don't have a cost from one particular node to another particular node, it is represented as a infinity. And when I am not having its own direction, it is reflected as a 0. So that is the reason here we have reflected as a infinity representation. So here I am going to write each and every vertex which gives a minimum cost. So S to A I have traveled. So S to A the cost is 6. Again, so let us see this graph particularly. So when I am traveling from S to A, the value is 6. Again, I wanted to calculate weight of A also. So now the weight here, the S infinity will be as a S weight will be 0 and A weight will be as a infinity. So now when this cost is moved from S to A, the vertex A allocated this 6 weight. So now A weight will become as a 6 and S weight will become as a 0. So S to the weight of A, now it will become as a 6. Again, from A to B, I am traveling. So now the cost is 9. So now B weight is infinity. So now when I am adding, so from A to B, it is traveling again S to A and A to B. So that means we wanted to add 6 plus 9. So that is nothing but here the value will be 14. The B weight will be 14. Again, same thing. So from here, again it will travel from one place to another. So like that, we will calculate each and every node weight. So we have a formula. So like this we will calculate each and every vertices. So like this we will add each and every vertex weight. So before that we will write the, in order to identify easily, we will represent a matrix form. So like yes, A, whatever the vertices are there, whatever the edges are there, we will write and we will reflect in this form. So here also S, A, B, C, D, E. So like this here we can easily understand. So S to A we have no connection, and S to S we have no connection. S to A we have a 6. S to B we have 9. S to C no. So it is represented as infinity. S to D we have a 8, and S to E we don't have any connection. It is reflected as infinity. So like this we will represent a matrix form. So by this matrix form we will calculate each and every vertex weight. So the minimum distance we are calculating all the vertices is like S to A and A to B and S to D and C and S to E. So this is a final path. S to A and A to E, and next E to D and D to C, C to B. This is a final graph which is obtained by using a Dijkstrastra algorithm. So like this, we will calculate each and every graph of vertices and the weight of particular vertices. And here it is another example. So here each and every weight of graph is calculated. Every vertices graph is calculated. So here Flody-Wall shell also here we will calculate like this. So whenever we are representing in this form, so here we can assign like this by this graph we can estimate that like we having a connection or vertices cost 1 to 4 is 1 and 1 to 2 is 8, 2 to 3 is 1. So like this, whenever we same it will be represented in matrix form. So here whenever we wanted to find the path from 1 to 2, we will avoid first row as well as a second column. So that means we wanted to travel all the vertices 1 to 2, 1 to 3 and 1 to 4. Again same 2 to 1, 2 to 2, 2 to 3, 2 to 4. Again 3 to 1, 3 to 2, 3 to 3, 3 to 4. So like this, each and every indication we wanted to check and each and every cost also we has to check. So like this, we will represent all the matrix. After calculating, we will get this kind of a matrix for each and every identification. So then the time complexity of this thing is big O NQ. So the Flody-Wall shell, it is also represented as a for spare graph and John's algorithm is more suitable. So most probably all pairs algorithm, it takes more time complexity. So here we will have a lot of space complexity is more and time complexity will be more for a all pair shortest path, and single source is shortest path. As we are analyzing about only single source or a single vertices, so based on single vertices only it is analyzed for all other vertices. So in order to calculate all those things, the time complexity we has to analyze as well as the space also we has to analyze. So this intentionally related for a greedy algorithm. So we have multiple solutions. So in that multiple solutions, we have specifying, we have optimizing our own desirable solution. Thank you.